Hey everyone, my name's Robert and I teach deep learning here at SAS. Today I want to talk to you about a really important topic called transfer learning biases in deep learning. Transfer learning is where you extract information from one setting or domain for use in another setting or domain. And this is very popular in deep learning. However, if you're not careful to reconcile the biases in transfer learning, your model performance can degrade. There are several types of transfer learning. There's supervised transfer learning, unsupervised transfer learning, and semi-supervised transfer learning. Today, I'll show you an unsupervised and supervised approach for reconciling differences in your source and target data. Now, the transfer learning biases that can arise fall mainly in two categories. The first is the frequency bias. The frequency bias occurs when a feature is not independent of the domain. That means that the marginal probability distribution of that feature is going to change across domains. So if it's not independent, if the feature is not independent of the domain, when it changes from one domain to the other, the marginal probability distribution can change. And that's a problem. To give you an example, consider a hospital domain and a business domain. And let's say that you're looking at the task of natural language processing. Words, terms that are independent of these domains would be something like road, table, person. Those words are likely going to be used at the same frequency whether you're in the hospital domain or the business domain. But words or terms that are not independent of the domain would be something like, in the hospital domain, maybe heart, patient, lung. In the business domain, it could be profit, customer, sales. Those words would be used at different rates dependent upon their domain. So your marginal probability distributions are going to be different. So when you extract that information from the hospital domain, those words, those conversations to be used in a business domain, you've got to reconcile those marginal probability distributions or your model can suffer. So that's the first bias, frequency bias. The second bias is what's referred to as context bias. And context bias is a situation where the conditional probability distribution changes across the domains or across the settings. So to give you an example, thinking back to the hospital domain and the business domain, let's think of the term positive. In the business domain, positive has a positive sentiment with it. Growth was positive this year. We had a positive response from our customers. But in the hospital domain, the word positive maybe has negative sentiment. Your test results came back positive. Unless this is something like pregnancy, the sentiment associated with the word positive could be negative. So you can see how the underlying relationship changes across the different settings or domains. Another good example would be small. The meeting room was small. That's bad, negative sentiment. The cell phone is small. That's positive sentiment. That's a good thing. So now I'm going to draw out two ideas using an unsupervised as well as a supervised approach for reconciling the differences in the marginal probability distributions. So here, this first model that I'm going to draw out, and forgive my artistic work because it's really not that great, is going to be an unsupervised approach. So we've got inputs on the input layer. And we've got inputs on the output layer. So this is an autoencoder, and we have another video on autoencoders, so if you have any questions, don't hesitate to check that out. So if you're using an unsupervised approach and you want to reconcile the differences between the marginal probability distributions between your source and target data using an unsupervised model, you would want to combine your source and target data. So here's our source. It's an R, source, plus target. So you would use both your source and target data and your autoencoder. And you would extract features that are capturing information that's present in both the source and target. That's the idea. That's what your goal is. Have that unsupervised autoencoder extract that information that exists across settings. This is also very valuable if you have a limited amount of target data. and lots of unlabeled, I should say, if you have a limited amount of labeled data and lots of unlabeled data. So this is a really powerful approach to use in that kind of a situation. If you have a supervised model, of course, you're going to have inputs on your input layer, and you're going to have, that's a Y, you're going to have an output on your output layer. So I'm going to build just a simple representation of a model here. So we've got fully connected, or dense layer, there we go. So in this setting, you would first train your model on the source data. And you're going to take those weights from the model trained on the source data, and you're going to freeze them, meaning you're going to share them with the target data. So you're going to freeze those weights and use those weights in perhaps the same model structure, but apply that model structure to the target data. But we haven't reconciled the biases yet. To reconcile those biases, we need to have what's referred to as adaptation layers. These are layers that are either added with learnable weights or layers in which we unfreeze the weights and allow the weights to learn to reconcile the differences. Now, a common question that's asked, which layers should I freeze versus unfreeze? Should I freeze the layers closer to the input layer? Should I freeze the layers closer to the output layer? It really depends upon the problem at hand. If the task is the exact same, so let's say you're predicting sentiment analysis, a binary target for sentiment analysis, and it's natural language processing, but you're looking at different domains. Maybe it's movie reviews that you're extracting from the source data, and the target data is your company information, where you're looking at sentiment analysis and conversations. Well, the task is the exact same, but the information at the input layer is significantly different. So in this setting, you would want your adaptation layers to be closer to the input layer, meaning the layers closer to the input layer need to be unfrozen. You may also want to still add in a few layers closer to the output layer, a few adaptation layers closer to the output layer. That's good practice, just allowing any further reconciliation to occur. So those are the two ideas that I wanted to share with you pertaining to how to correct for transfer learning biases. You've got frequency bias and context bias. These occur in transfer learning. These can degrade the performance of your model. So I hope I've given you some good tips or tricks that you can use to mitigate these occurrences. Thank you for watching. Check out the links below for more information. Please leave your comments and questions and I'll get back to you. And if you'd like to see more of these videos, definitely subscribe to our channel. Take care.